My name is Mia Snyder, and I am the Outreach Coordinator.
Hello, my name is Aneesh Singh, and I am the Design and Video Supervisor.
Hello, my name is Marissa Cuevas, and I'm the building supervisor.
Hello, I'm Ishan Dutta, and I'm the coder.
We are all juniors in the engineering program here at Eastern Tech, and we are your Wearable Tech 2020 to 2021 team.
Along with us team members, Ms. Waldrop served as our advisor for this challenge.
Hello there.
For our challenge, we were required to design a wearable neonatal health monitoring system to monitor the respiration rate of a baby. To do this, there were many parts that had to be achieved.
We had to use hardware such as sensors and microprocessors to sense chest movements in an infant. We also had to write a code to output respiration rate on a display device located at least 27 inches from the infant.
Before we got to the design process, we had to do some background research. One main thing that we looked at was the field of ergonomics, which was the study of making sure that a device is comfortable to use and flexible.
Ergonomics was a very important factor to consider for the design aspects of our project, since we had to make sure that the respiration monitor was comfortable for the baby while still being able to produce effective results.
Aside from ergonomics, we looked at the importance of respiration. This biological process is a crucial bodily function. It involves the production of energy, usually by the intake of oxygen and the release of carbon dioxide. In other words, it's the action of breathing.
Have you ever tried deep sea diving or tried holding your breath? Now imagine a baby in that same scenario. If a baby were to be sleeping and unable to breathe properly while the caregiver was unable to intervene, the neonatal health monitoring system would be able to alert that something was wrong immediately.
Our challenge, we also corresponded with experts. Individuals from the sleep monitoring company, Phoenix VA Healthcare, provided us with key information about infant breathing patterns and key things to look for with their respiration. Some of these things included patterns of breathing and placement of the device on the child.
For our design, we have chosen it to place it on top of the corresponding part of the child that mimics the diaphragm. This is crucial for the placement in real life due to the fact that if placed incorrectly, it can cause harm to the child.
The screen to the left shows our meeting logs and what we accomplished each meeting. As shown, this was a group effort where we all contributed equally to the success of this project. This was a slow and steady process over 4 months. The first part of our design process was the creation of a preliminary sketch for how the breadboard and seatbelt would look in order to fit our criteria. As shown, we were sure to add dimensions. There were many design choices for our seatbelt design, which contained the breadboard for the neonatally. One idea, which is to the bottom left, was to sew a magnet into the cloth on both sides of the seatbelt. Another idea, which is to the top left, was to utilize clips.
We were able to 3D print a device to secure on the breadboard. As shown on the screen, we had multiple design choices to choose from. After much collaboration, we ended up choosing the design to the left due to its keen ability to secure the breadboard while maintaining a comfortable fit on the baby. This design was able to fulfill all ergonomic requirements as well, with its use of felt and nicely placed fastening methods.
For the seatbelt, which was wrapped around the neonatally and contained the breadboard, felt fabric was used. As mentioned previously, we used clips as a fastener. It was important for the seatbelt to be comfortable as well, since we did not want to choke the baby.
We originally planned on designing the seatbelt so that it was secured with magnets. However, during the design process, we changed that to a buckle since it was much more secure for the baby. As shown on the screen, there are three main parts of the final design: the Circuit Playground Express, the neonatally, and the belt buckle. The neonatally is able to replicate the respiration process of a baby and how quickly it can change. The circuit board is able to sense these changes through an accelerometer and display the breaths per minute on some sort of software like Notepad or Word. Finally, the belt and its buckle hold the circuit board on the baby so that it will not fall off during sleep.
One obstacle that we faced concerned the dimensions of the 3D printed device and how it used to hold the breadboard. When it was printed, the 3D printed device was too large for the breadboard. We fixed this problem by placing hot glue along the edges of the device so the breadboard would be secured.
Another major obstacle we encountered was completing the project strictly virtually. This limits our access to materials, makes it difficult to collaborate with team members, and requires us to go back and forth to transport materials and equipment.
To demonstrate how to put the belt on the neonatally, you simply place the breadboard on the baby's chest and clip it in the back.
We chose to use this clip because it is easy to use and any caregiver will be able to take it on and off of a baby without difficulties.
There were two ways we tested our design. We ensured that the seatbelt went around the entire circumference of the neonatally, and we also made sure that the breadboard could sense the upward chest movement of the neonatally when we pumped air into it.
So there's a few components that we need to look at. First, this forever loop right here. This creates the accelerometer function using the z-axis, of course. Then these two components right here, the on, start, and forever. This is the timer. It sets the timer in seconds to 0, and then every 1 second, which is 1,000 milliseconds, it'll increase it by 1, and then convert this seconds timer to minutes, and then it'll use the minutes timer to set the variable, set the breaths per minute variable, which is also the respiration rate, and then it'll display it onto whatever software you want to use. And then this right here, if you click the button A, then it'll reset the entire timer, and then this is useful for testing. So the way the accelerometer works, it starts at about -1,000. So if you move it up, then it'll increase. So at about -985, I set it so that it'll indicate that it hit a certain point, and then I changed the breaths by 1. So at about -985, that's the amount of one respiration, and then otherwise it'll just show a red display board. And here's an example. This isn't the actual device, but see, it starts at about -1,000, as we can see, and then every time it is touched or moved, then it lessens significantly. It's going to be a live testing of the program and the efficiency of our project. That's our display board, and this is, of course, the device, and here's my stopwatch. I'm gonna try to pump it 60 times in 1 minute, and then we'll see what our final respiration rate in RPM will be by the end of it. Kill the program. Okay, let's see what we got. 89. It's pretty good. 19.
The first criteria we had to meet was that the respiration device was able to fit on the baby properly. The second criteria was that the device was made of infant-friendly materials. Marissa showed that the breadboard measuring the respiration rate was able to be fit on the infant properly and securely. She also showed that the material we used for the seatbelt holding the breadboard was appropriate for the infant because it was soft.
The third, fourth, and fifth criteria was that a hardware could measure the baby's chest movement, information was able to be gathered from the sensors, and that the respiration rate on a display was 70 centimeters away from the baby. Ishan showed in his segment of the video that the circuit board was powered by the AAA battery and could properly measure the baby's respiration rate. Finally, he made sure that the neonatally baby was 70 centimeters away from the screen that displayed the respiration rate.
The final criteria was that the cost of materials was less than $50. The only thing that was bought was the fabric, the thread for sewing the buckle for the seatbelt, and the 3D printed material for the circuit board holder. The buckle for the seatbelt was about 37 cents from Amazon. The felt fabric was about 24 cents from Joann's Fabric, as well as the 30 cents of the thread. The 3D printed material cost about 36 cents from Micro Center.
While working on this project, I learned how the accelerometer worked when coding. Along with this, I was able to decipher the different blocks aligning with our chosen program MakeCode.
I learned the full extent of research and how it applies to the design portion of the engineering design process. Being able to talk to professionals opened my eyes to all of the obstacles that we would have to overcome if we were to produce and distribute this device into the market. One thing we could improve next time is transferring the respiration results directly to someone's phone rather than their computer screen. This allows for more accessibility and practicality. We also wish to ensure a more sleek design rather than bulky. Overall, we are very satisfied with our final design.
To measure how accurate our respiration monitoring system was, we used this accuracy score formula to figure that out. So we do the absolute value of the actual observed rate minus the reported rate. Using the formula, we do 89 BPM minus 60 BPM and take the absolute value of that, giving that our accuracy score is 29.